Um, okay, I think we can get started. Uh, I think people can join as they log in. So once again, good morning all. Myself, Manjunath. Um, Along with me, we have Raj, Veronica, Bhagyashree, and Sai from Webster. So just quick introduction about Webster. So we are basically into corporate automotive training. So we have been providing the trainings to various automotive industries. That could be a OEM or a tier 1 or a tier 2 company. Um, you can head to Webster's website and you can explore more in terms of what we do and what kind of services we provide. Okay. So yeah, about me, I see a lot of participants whom I'm already familiar with. We have somehow interacted one or other way. There are a lot of other participants who are new and yeah, they kind of they might not have interacted with me previously. So myself, Manjunath, I have 12 years of experience working in automotive industry. I have worked with various companies like Bosch, Harman, Qualcomm in my past experience, and I have been in a training business since last few years, where I have been delivering training on most of the automotive topics. Okay, and let's get started with today's agenda, why we are here and what all things we are going to cover. Yeah. Hope all of you are able to see my screen. So this is the agenda for today. Future scope and need for automotive engineer, right? So there is a trend which is starting where a lot of people, right, who have an embedded background, they are kind of trying to make an entry into the automotive industry, even the freshers, right? So they have already decided, they know where they want to build their career on, right? So what is the scope what we have in the automotive domain? Right, so we'll try to understand that. And when we talk about automotive, definitely Autosar is something which is the platform now for any engineers to get onboarded and start contributing or working. And why Autosar is important and why you should learn it. So it doesn't really matter whether you're working on a driver layer or application layer or maybe intermediate layers, right? So, but still you will be somewhere, will be part of the Autosar. And how can you learn Autosar step by step? So it's a huge architecture. So you cannot expertise Autosar in a very short term. It has its own learning curve, and it demands a lot of time to expertise on a different module. So how do we approach uh, and how do we learn this step by step systematically and become an expert, right? So how do we do that? So that is something which we'll try to understand. And definitely the skills and the tools trending in the automotive industry, will try to take a look at that. What are the alternatives available in the market, right? Definitely we'll give a glimpse on that, so that it's not the only technology or the concept or the architecture which we should learn. Definitely there is a tools and tool chains and the skills which we also need to develop alongside. And what would be the learning journey for automotive software professionals, right? So from where they start and where they end, what are the knowledge gaps they need to identify themselves along with the industry? How do we keep up with the industry, right? And how do we bridge that gap? And how you can continue the learning journey with us in the automotive domain. What are the various topics we are offering and what is the mode we are trying to operate, right? So yeah, we'll try to go through all of this, not like an individual slides, but basically I will go through these topics as we go through the short session on the Autosar as well. So the people who have joined today, they are definitely will go through a short session on the Autosar. Through that session, we'll try to address these points. We'll not try to cover both the topics differently. We'll try to cover both together, right? So that you also get a understanding and a relation with respect to the Autosar and all these agenda points. Okay, so yeah, we'll get started. So maybe before that, I just want to highlight one point. the reason why we are here is we have been doing various trainings in past. Maybe that could be dedicated a CAN training, CAN TP, CAN FT, CAPL, or maybe a Kano tool or a Autosar training itself, Davinci Configurator, Davinci Developer, or it could be a Lin FlexRay, right? So these various trainings are delivered in past as a open house training or a corporate batches, but there has been a demand where people want to kind of combine all these trainings and transfer themselves to a embedded engineer into an automotive engineer, right? So for that, we have come up with a course which is for a duration of a 1 month, specially curated for the working professionals, right? Where they can spend an effort on the weekends and maybe a few hours on the weekdays and collaborate, create a community, learn, and exchange the information. How do we do this, right? How do we uh, um, do this? So for that, we have this curated course which has all the various topics which I'll discuss in future, and along with that, you'll get a Autoverse certification which helps you uh, um, with a with the acknowledgement saying that okay, you have gone through this training. It's not only the participation or the attendance, but also you have cleared all the various tests, which is a theoretical as well as the practical, which you have cleared, and which says that okay, you have expertised these topics. Okay, so yeah, that is something which we are launching, and that would be the first yeah, this would be the first batch. Whoever willing to participate, take up that course, they can take up. And how do we do that? Maybe at the end of the course we will tell. Yeah, so let us get started with the scope part, right? So before we understand what is the scope for the automotive engineers in the coming years, first we need to understand what is the scope for the automotive industry. What is so if you need to understand the future of automotive industry, we kind of need to look back and see what has happened so far, right? And with that, we can try to predict what is going to happen in the future, right? So I believe a lot of people who have joined on this call are coming from the automotive background, and they are kind of contributing in one or other area. Yeah, but if you look back maybe 1975 till maybe 2020, a lot of things have changed, right? If you go back maybe a 50-year-old car, probably you'll not even see a single ECU. It is completely a mechanical system, right? And there is very minimal electrical parts involved in that, and there is not, almost you not see no electronics, right? You may till today also in India you may find an old Jeep. If you open it up, you hardly see any electronics in it, right? It is completely a mechanical system. And there was a need, right? There was a need which started to have the electronics into the vehicle, and this need emerged out of various requirements which a mechanical system could not fulfill by itself, right? So in the early 1980s, 1960s, 70s, it was the efficiency, which was fuel efficiency, which was a bigger challenge, and people were not able to address that by fine tuning the mechanical system, right? So mechanical system always has its tolerance, and it always has its wear and tear which comes with its the age, right? So how do we fix this problem? So it was only possible to achieve with the electronic system, right? So that is where the fuel injections came into the picture, because the efficiency of an internal combustion engine, whether it is a diesel system or a gasoline system, it all depends on how much fuel you inject, how precisely you can control the fuel, and how precisely you can control the timing at which you inject the fuel, right? And this amount of precision, so when I say this amount of precision, it looks very simple maybe when I talk about it, but maybe if you go to IC engine and study, I hope most of you have studied the internal combustion engine, the two-stroke engine and the four-stroke engine. There is again engine idle RPM, right? For any car, the idle RPM is around 800 to 1000 RPM, and when you are running at a high speed, it goes into thousands of RPM, right? Which translates to how many times a piston is going up and down into a internal combustion engine, right? So you have a tiny amount of fraction of second where you have to inject the required amount of fuel. Also you can control the amount of fuel you are injecting, right? There are a lot of things which you need to control, and that is not possible, that was not possible just with the mechanical system. And that is where electronic fuel injection system came in, and yeah, we could control it very precisely, which helped us to improve the efficiency of a vehicle. Yeah, So that is how things got onboarded. The electronics got onboarded into the car. But once it got onboarded, people figured out that yeah, they can definitely have few more sensors or the actuators placed, and they can control a lot of various things, right? So the gearbox control, traction control, anti-lock braking system, cruise control, airbags, right? Safety features, emergency call, adaptive cruise control, active body control, right? Electronic stability programs, stop and go, curve warning, right? Hybrid powertrain, road trains, collision mitigation, automated parking, software updates, telematics, telediagnostics, right? So these are the various features which started uh, 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 getting into the automotive system, right? And once you have a kind of a ECU placed inside a car, you would definitely see with a very minimal hardware addition, or maybe sometime no hardware addition, right? You can tweak the software in such a way that a lot of innovations you can actually bring into the vehicle, right? So when you have enough electronics inside the car, it is always we always have a possibility of innovate inside the software and increase the efficiency or a safety or a functionality of a vehicle, right? So if you look at the innovations what has happened in last 2 decades, you'll see that 80% of automotive innovations are based on software. Yeah, definitely the hardware is evolving, but the innovations which are coming out, it's if you look at the IC engine, what we have today and what we had maybe 20-30 years before, it has not drastically changed. Definitely it has changed over the time, which has taken its better shape, but it's the same principle on which we are working, right? But the electronics which is built around that internal combustion engine, it has kind of evolved, right? And today we are at a hybrid and EVs, electric vehicles, where yeah, our the core powertrain itself is changing, right? But which doesn't mean that the electronics around it is going to disappear. It's only going to grow and grow more, right? Which means that to run that electronics, the microcontrollers, the chips, you would need a software, right? And this software is for a lack of better word, I would say that it is exploding, right? It's growing day by day, and there is a demand to include various safety features, functionalities, right? Efficiency parts. So a lot of things are coming in, right? So so if you take a example of any feature which is coming into, maybe I'll just give one example. Like you can think of many examples. What are the features which are coming into the vehicle, right? Today we are at a level 2, level 3 autonomous driving. The goal is to go for level 5 autonomous driving. We are still far. Probably there is a lot of scope or scope for the improvement, or the scope for achieving the level 5 autonomous driving. So a lot needs to be done at. So there is a lot of scope where people can come in and contribute, definitely. Yeah. So if you look at today's technology, where we have like a radar, lidar, or a laser. For laser, if you take an example, so nobody invented a laser thinking that that is going to be used in a maybe eye surgery, or maybe for a autonomous driving, or maybe for a aircraft, right? But the technology was invented. People figured it out that okay, that can be used to, yeah, maybe laser is an equipment which will help you to kind of penetrate to a 3D object and only look at a particular layer of atoms, or maybe a particular layer, right? That is how they used it in the optics, the laser surgery. They kind of burn a part of the layers into the eyes, right? The same was again reused in the vehicle, right, to detect the obstacle which is in front of you, right? So we never know exactly like what technology will seep in into the automotive, right? But we know what is our ultimate goal. We want to see one day a vehicle which does not have a driving seat. All the four seats are facing each other, right? And there is no driving seat. A vehicle which picks up you from the home and it will drop you to the office, and there is no driver in that. So that's the ultimate goal. So till we reach that point, there is no saturation which will happen in the automotive industry. And to achieve that, we have a lot of time. So that defines what is happening out, and what is the scope, and how do we can contribute, and how can we get prepared for this journey, right? Let us take a look at the ECU part, right? Which is the basic component which controls the vehicle, and it is not one component. There are multiple ECUs, right? So if you look at today's car, a home car, it has around 70 ECUs or so inside a vehicle, right? And if you go to a sports car, right, it would definitely have 200 plus ECUs inside it. And yeah, the number of ECUs are growing, and there is also a effort where they want to reduce the number of ECUs, where they can share the functionality of multiple ECUs, put it onto a high performance computer HPC, and try to get many things out of it. There is a hypervisor which is coming into the picture. Yeah, so this is where we are trending towards. But we started, if you go back to 1980s, we just started with one ECUs, and we had a trouble. How do we communicate with multiple ECUs? That is where the CAN protocol came in, right? We quickly hit a bandwidth constraint. We went ahead and we got FlexRay or a MOST protocol, which helps the higher bandwidth, right? We wanted a low cost protocol, which is useful for a probably say controlling a wiper or controlling a door lock or an immobilizer, right? Where the information carried is a very small amount of information, and we really don't want to parse or process that information. So we came up with a LIN, local interconnect network, right? We wanted something which is robust, reliable, and also which is of a high speed. So we got a FlexRay, right? CAN also kind of try to compete with all the other protocols. We got the CAN FT, which is the flexible data rate, which can go up to again a higher speed. The traditional CAN is 1 Mbps, CAN FT can go up to 10 Mbps. Yeah, most, yeah, it can go up to 100 Mbps. FlexRay can go up to 10 to 20 Mbps, right? LIN is a very low speed, it can go up to 10 kbps, right? So if you look at all these protocols, what I discussed so far, these were invented for automotive, right? So these protocols were not were used in some industry and then adopted to the automotive industry. So these were invented for the use case of automotive to solve the problems in the automotive industry. Yeah, for the first time we are gonna, like, we have already adopted it and we are adopting it, which is the Ethernet, which has proven its ability to be a robust and something which is reliable, right? So now industry is taking a turn towards adopting a Ethernet, which does not mean that the CAN will disappear tomorrow. No, CAN will have its life inside the vehicle for coming decades, but Ethernet will also play its role when the high bandwidth requirement comes in, or maybe it can act like a mother network or a backbone network where the OTAs can be handled over Ethernet. So there are various concepts people are trying to put in, right? So yeah, so in terms of communication also, you would see there is a lot of evolution which has happened. If you look at the bit size of the microprocessor, the controllers what we are using, so we started with a very basic 4-bit controller, and today we are at a 64-bit controller, right? So even the processing power of a microprocessor or a controller is increasing drastically, right? So today, I think 64-bit, it's not that every ECU which is there in the vehicle is of a 64-bit size. So we still have a 16-bit and 32-bit, and they are doing perfectly fine to carry out a dedicated functionality what is given to them. But also we have this ADAS which is coming in, which is demanding for the higher processing power, right? Where in a fraction of time you have to detect whether it is a car or a bus or a pedestrian and make a certain decisions. There's a computer vision involved, a lot of AI, ML, algorithm, everything involved. So there is a need where we have to have this HPCs. So that is where the 64-bit controllers or the processors are coming in and helping us, right? So we understand two things here. One is how the hardware is changing, how the communication protocols are changing, how the more electronics is getting into the vehicle, which means, in other words, which means the software which is driving today's vehicle is increasing tremendously, right? And it is also becoming more and more complicated. And we need kind of an architecture so that we can kind of put a boundaries to it and create interfaces and have it in a form which is reusable, which is modular, right? So that is where Autosar is coming into the picture. So it doesn't mean that Autosar is the first architecture which is trying to address this. We had a lot of various architectures which was used in the automotive industry, which were kind of specific to the OEMs or specific to the tier ones, right? Or maybe sometimes specific to a group of manufacturers, which could be a semiconductor on the tier one combinations, right? But yeah, they were all kind of dedicated to a certain group of people. But the industry very quickly figured out that this is not going to sustain or work for a very long time, and we need to come up with some open source architecture which is open to all the participants of the automotive industry, and they can contribute for this architecture, right? So that is where the birth of Autosar took place, and they have tried to address various challenges and have tried to meet various objectives, right? Let us try to understand what is the challenges, right? E&E complexity is growing fast. So just now we came through the journey, how the vehicle has evolved, the automotive industry has evolved. So definitely E&E complexity, which is electronics and electric complexity, that is increasing. Hybrid vehicles coming in, it is becoming more and more complex because you have to handle both the sides of the powertrain. Yeah, the quantity of software is exploding, right? The amount of lines of codes which are running inside the ECCU, right, it is tremendously increasing, right? So I always give this example or ask this question. So if you compare a number of lines of a code which is running inside a one car, maybe a home car or a sports car, if you compare the number of lines of codes running across all the ECUs of that vehicle with a maybe a Boeing or a Airbus, right, aircraft, so which has the more lines of code? I don't know if all of you have access to the chat. Maybe if you have, maybe you can just type it over there. If not, I'll let you know in a few seconds. Yeah.
Veronica, you can just turn on the chat box for the participants.
Yeah, so it always looks like the aircraft is more complex in nature, and yeah, it definitely need to have a lot of functional safety aspect associated with, so that because it is carrying a huge number of lives on it, and any kind of risk will directly put you into a hazardous situation where someone can lose their life, right? But the truth is, the number of lines which are running in an ordinary car has a huge more number of lines of codes than compared to an aircraft, right? Yeah, there is a reason why it is so. There is a lot of software redundancy which comes into the vehicle. There are a lot of functional safety aspect, because when the aircraft takes up, it has fairly a simple operational mode where it really need not to change much, right? But when you take a maybe autonomous car, it has lot. It is not going through a air, it is going through a road, and there are a lot of things which can happen suddenly, right? And you have a lot of piece of code which maybe you might have written by yourself, which is sitting into the else part of the code, right? If is always small, we understand. If is very like simple, if this happens to this, but the else part of the code, right, it is always growing, right? You want to ensure that nothing breaks. You want to take all the possible recovery mechanism, fail safe mechanism, right? And that makes the code more complex and much bigger, right? Yeah, to cut short, yeah, the automotive system or a vehicle has more lines of codes running on it compared to aircraft. Many different hardware platforms are used, right? So this was one challenge where you have a different hardware platforms used across the different OEMs or a tier ones, right? There are different silicons, right? There are processors, controllers, there are ARMs, there are x86, right? So yeah, people have tried to push even the x86 for the infotainment system using the ARM for powertrain, right? A lot of things, various things have tried, and different architectures or the hardware platforms have come, right? But altogether, as an automotive industry, we are not kind of focusing or putting energy into a one platform, right? So how do we address even that? So that is something which is today's challenge. And even the development process and the data formats, they're not harmonized, right? The tools which are used across the industries, different OEMs, different tier ones, the data formats. When I say data formats, how do we exchange the information between two ECUs, right? How do we exchange the information between two OEMs, or the OEMs and the tier ones, or the two tier ones, right? So these are not standardized, right? People still use a maybe Excel sheet or a PDF or a document, right? We also have a very famous DBC and the CDD file. We try to break that by introducing the ODX file, which is an open source, right? CDD and DBC are something which is a proprietary to vector, and if you want to use that, you need to have a vector tools. And again, yeah, it kind of vector has its own ecosystem. Once you get into that, you always tend to use the CDD and DBC, and yeah, they come with certain advantages where like you use the CDD to generate the DAG stack and DBC to generate the CAN stack, and use the same thing in the Kanoi to build some scripts, or the CAPL, write some CAPL scripts. Again, use the same thing in CAN Jenny to generate a non-Autosar stack, or maybe in the configurator to generate the Autosar stack, right? So yeah, so that has that. And ODX, yeah, never broke it into the system very widely. It could not penetrate, but soon Autosar came in, and yeah, they have this standardized data format, which is the ARXML, the file in the automotive in the world of Autosar, right, which kind of helps you to put all the information into a certain tags, certain format, which is maybe not human readable, but definitely a tool readable, and it will help you to configure, right? We will also see how that is helping. Yeah, so the main objective of Autosar is to improve the software quality and reduce the cost by reuse, right? So as we go through, definitely you'll understand how this is becoming a very modular software, so that it can be reused, because it's all standardized and all interfaced with a standardized interface, right? So definitely reuse will reduce the cost. And how does the software quality will increase, right? This is always a slightly I'll not say easily convincible to every automotive engineer. If I adopt to Autosar, how does the software quality increase? Because Autosar is not going to give me a, it's an open source architecture. A lot of people have this misconception that, okay, if Autosar means they will also provide me a source code, right? So it is not a open source code, it is the open source architecture. So please try to understand that. Android is an open source project, right? Open source, you'll get a code there, right, where you can build the you can take the AOSP, Android open source project, and build a product out of it, where you have a lot of code which is available, right? So if you use that, the code which is already being used by various in the mobile world, right, it is already being used by the various products, and the Google itself have tested it. So definitely quality goes up. Yeah, definitely quality goes up. But here Autosar is not giving you the source code. They're only giving you the standardized software. So how does the software quality is going up, right? So once you build this modular software, and if you start reusing it between the different product lines, variants, between like across the world, right? People are using the same CAN interface, CAN driver, right, which is built under the same specification. So as a software module, as a specification, it is evolving, it is becoming more and more better. And the people who are supplying these modules, they are also improving, and they're making it more better and better. And there are millions of vehicles who are already using this software, and which is running on the road. And if they report any bug, it is not going to fix only for that vehicle, it is going to fix for all the vehicles which are running on the road, all the vehicles which are under productions, all the vehicles which are under planning, and even the specification itself will have an improvement or the fix if there is a bug, right? So in that way, you're always referring to a software module or a specification which is not frozen, and it's the like kind of done and dusted. No, it's come every day, it is changing and it is evolving. So you are always improving your software quality by using the Autosar architecture, right? Reuse of functionalities across car lines and across OEM boundaries, definitely you can reuse because it is modular. The development methods and the tools, yeah, there are a lot of tools providers who are coming in after this Autosar, right? So who are providing the different tools. How do we tools can be built around the ARXML? So that is something which is reusable, the development methods and the tools. And the basic software, we'll try to see what is basic software. Most of you know it. Yeah, that is the basic stack what you have in terms of maybe DAG stack, COM stack, MEM stack, which does not really hold a functionality or the application function, right? But it includes a lot of basic functionalities which are required to access the hardware, or to write some logical code in the application software, which calls this base software, which is common across, mostly it is common across all the ECUs, right? So yeah, so that is something which can be reused. Yeah. So yeah, to start with Autosar, it is automotive open system architecture. As I said that it is something which is a worldwide development partnership between the car manufacturers, suppliers, and the semiconductors and the software industries, right? So they all have come together and they decided that, okay, we need to finalize on some architecture which we can put our time and money and work towards it and make it as a some global standard where everybody can kind of adhere to it, right? So this all started long back, and a lot of big companies like Daimler, Volkswagen, BMW, Bosch, right? So all these guys came together and they kind of created the core members, right? So these are the 9 core partners. So again, this changes year by year. A lot of premium members or the development members, right, who are coming in and they're trying to contribute. But basically, core members have a final call, or maybe they kind of listen to the industry's need and decide what will get into the next version of the Autosar, right? And what we will drop. So there is always some things which are getting outdated, we remove it, and some things which are in a high demand and which is required in almost each and every ECU, right? So which is getting added. So yeah, this is the Autosar consortium, so called, what you can call it as. Yeah. So it has the OEMs, it has the generic tier ones, it has the standard software providers, it has the tools and service providers, and it has the semiconductors, right? So although it is a software architecture, why do we have a semiconductors here? Because they are the one who actually provide you all the basic drivers, so-called MCAL in the Autosar, right? So we'll also see that. So all the semiconductor providers like Renesas, NXP, Infineon, right? So these guys give you a lot of MCALs on which you can build your BSW and configure your BSW and the right application software. So they also equally play an important role when it comes to a Autosar. Yeah. So if you look at the Autosar specification as such, from Autosar 3.2.1, yeah, maybe today we have Autosar 4.4, right? We also have the adaptive Autosar, which is trying to help the infotainment part or the ADAS part, right? Where we need a POSIX based operating system, right? So if I take Autosar 4.4 specification and if I print it, right, on a A4 sheet, and if I stack it next to me, it will cross my height. Yeah. So my height is like 5 feet 11 inches. So it will definitely goes above 6 feet. Right. So those are the number of pages which has been written, documented, and made public. Right. Right. What are these documentation? This documentation has a very clear definition of how a software component should behave, what is its requirement. There is a SRS and SWS, software requirement specification and software specification. Not only that, but also the interface name, exact interface name. In other words, C function name, the arguments it takes, the return value, and the range of the argument. So this is very well clearly defined inside this specification. And the second important aspect is the configuration, right? All the configuration parameters, there are thousands and lakhs of configuration parameters which are defined in this document. And if you change the value of that configuration parameter, how the functionality of the software changes. So everything is very well defined into this document, right? And so this would be your Bible or a guide. If you are in a doubt, if you really don't know how a particular configuration parameter behaves, what is its effect on the other components, right? There's a multiplicity, there's a lot of various factors. When you go into this document, you'll understand. So how do we approach it, study it, right? So yeah, so it is not something a study material. It is something a reference material. I'll always say that. Yeah. So once you know the Autosar, you come to this document and try to enhance your knowledge. Yeah. So yeah, just a comparison, yesterday's software and what Autosar is bringing in, right? So if you take, if I simply give you a one simple microcontroller and ask you to write a software where you have to blink a LED every 1 second, right? It hardly takes 5 minutes for you to write a loop, while loop, and toggle that with some sleep time, and you use a corresponding pins address, write a pointer, and you do that, right? So your software is up and running in a 5 minutes. But tomorrow, if I say that, hey, I want to reuse the same software, but this time I want to run it on a different board, right? So our software will not directly run on that, because we have already done that star P and we have assigned the address of a particular pin of that microcontroller, and that address is not same in another controller, right? So this has been always a traditional problem, and we have tried to solve it in a various different way, but it never could hit a 100% modularity, where the Autosar is trying to bring in that, where they want to differentiate the hardware, the MCAL, the issue abstraction layer, the service layer, then the RT, then the application software, right? Right, so this is I have just put a one picture which shows a lot of various components, right? Just to go through, maybe, yeah, maybe most of you may be aware of a CAN, like if you look at the CAN interface, right? So CAN SM, CAN NM, CAN TP, right? So all of these are the different modules inside the CAN which represent the certain functionality of a CAN driver, right? Similarly, you have that in the diagnostics, you have the DCM, DEM, FIM, which represent the certain functionalities or the behavior, owns a certain behavior or the functionality of a diagnostic stack, right? Yeah, if you look at the market evolution, the number of OEMs using Autosar is growing. Yeah, there are a lot of OEMs, even the OEMs who are so-called as the into the entry segment of the vehicle, or maybe who are contributing to the emerging market, especially the Asian market, maybe India, China. Yeah, yeah, even they are kind of coming towards adopting the Autosar because they understand what is the benefit. Yeah, number of tier ones who are using Autosar is growing because they understand the benefit, because they need to build it once and they can sell it multiple times with only the configuration changes. The Autosar functionality itself is growing. It's not that Autosar is defined and yeah, it is there. No, every day it is getting refined. We have new stacks. We got a crypto stack, we got a wireless communication stack, the two new verticals added to the Autosar architecture, right? The investment for the tool providers to support the Autosar is growing. We have a lot of tool providers who are helping us to get this done, right? Yeah, and alternative solutions what we had so far, right? They are losing their ground and everybody is kind of moving towards Autosar. So market is certainly growing at approximately 20% per year. This is a overall number when it comes to the car. Again, if you bring it down that number to a various components, yeah, it varies. Some guys are going at a rate of 50%, some guys are going at a rate of 10 or 15%, right? So consolidated, you can say at 20% is the approximate number by which the market is growing. Yeah, so let us take a look at the Autosar itself as a layer, right? So predominantly it has three layers. If you take a look at here, one is the hardware layer, definitely microcontroller, and then comes the basic software layer, which is the first software layer of the Autosar, and then the runtime environment, which is the layer which differentiates the application software and the base software, so called as BSW and RT. Sorry, BSW and ASW. ASW is nothing but which is above the runtime environment, which is the application software, right? So the style of arrangement in the BSW is something called as module wise. You have different modules placed one above another, which is called as the layered architecture. The style which is followed in the BSW is the layered architecture, which will help you to break the dependency, or kind of become independent of the hardware, right? As you go or move up in the software stack. So that is what is the basic responsibility of the BSW. Whereas when you go to the ASW, the style changes from layered architecture to a component architecture, right? Where we have a different software component which are independent of the hardware or the ECU on which they are running, but they demand a certain interfaces or the information. Once that information is provided to them, they can independently process and give you the desired output, right? And these two style of design is differentiated or separated by a layer called as runtime environment, which is RT. Okay, so let us try to understand a few of these layers. 1 second, give me 1 minute. So yeah, so let us try to understand what are these layers, what are their roles, and how they are helping to build a software layer which is independent of a hardware, right? The first most or the bottom layer in the BSW is called as the MCAL, which is microcontroller abstraction layer. Okay, so this is the lowest layer of basic software, and it contains basically internal drivers, okay, which are the software modules with direct access to your microcontroller and the internal peripheral. Okay, so when I say direct access to microcontroller and the internal peripherals, so it means that all the subsystems or the components which are part of the microcontroller, which could be a timer, which could be a interrupt, which could be a internal registers, your GPU, CPU, your memory, right? All these are called as your internal peripherals, right? Which could be sometime maybe a UART, CAN, SPI. So how do you control this hardware, right? You need a piece of software which can sit on top of the microcontroller and control this. It is as simple as that. So that piece of software is nothing but called as the MCAL, and it has a direct access to the hardware. And the task of this layer, right? So you will always see these two things coming up for each layer, task and the properties. So if you try to understand these two things, you'll understand what is that layer doing, right? Or why that layer is present. So the major task of this layer is to ensure that make the higher layers independent of the microcontroller. So this layer, the job of this layer is to ensure that the underlying microcontroller, if it changes tomorrow, today you're using maybe suppose say that maybe Renesas RH850 or the V850, and you want to change it to maybe another version of from V850 you want to move it to RH850, or maybe the Infineon TC2752 or 277 or something like that, right? So you want to kind of change it. So the job of the microcontroller abstraction layer is to ensure that the above layers are getting unaffected. You can just change the microcontroller, swap the microcontroller, but any layers above that shouldn't not get impacted, right? So that is the major task of this particular layer, right? And it has two properties. If you look at this layer, the implementation in the upper interface. If you try to understand this, you'll get a more insight on what exactly it is, how it is built, and what exactly it is doing. So the implementation of the microcontroller abstraction layer is microcontroller dependent. Is that right? Because if you are trying to control a particular resources, peripherals, right, or the modules inside the microcontroller, definitely you need to know the address, right, of those registers, pins, ports. So which makes the implementation of the microcontroller abstraction layer dependent on that particular microcontroller, right? But whereas the upper interface, right? The second point, the upper interface, which means that if you want to send a CAN message, right? CAN underscore TX or RX, right? Or if you want to send a UART message, or you want to set a particular pin of a microcontroller, right? DIO pin. So right, that interface name is something which is first word you see here, standardized. The moment you see the word standardize, it means that it is present in those Autosar specification, what I shown you before. Somewhere in the one of the software requirement specific software specification SWS document, this particular interface is defined. You exactly know the name of that C function, what is the argument it takes, what is the return value, right? So first thing is it is standardized, and second thing it is microcontroller independent. So whether it is a TC277 or whether it is a RH850, it really doesn't matter, right? To set a particular pin, the interface what you are going to use from the ECU abstraction layer, it is going to remain same, right? So this is how it is achieving that independence from the microcontroller, right? So I will just quickly repeat. The task is to make sure that the higher software layers are independent of the microcontroller, right? And how does it make it? By making himself dependent on the microcontroller, but the upper interface, which is standardized, right? Making that interface independent of the microcontroller. Is that clear? Yeah. So quickly we'll go and try to apply the same logic to the next layer, which is the ECU abstraction layer. So now inside the ECU, you have a microcontroller and you have a MCAL, which is running on that particular microcontroller and controlling all the internal peripherals inside that microcontroller, right? And now what is the job of a ECU abstraction layer in that case? What it controls? Whatever is inside microcontroller, it is already being controlled by the MCAL. So what is this ECU abstraction layer? What additional functionality it is bringing in, right? If you ask that question to yourself, the answer is, yeah, it offers an API, right, for access of peripherals and the device regardless of their location, whether they are internal or external, okay, and their connection to the microcontroller ports or the pins, which means basically you have a lot of components which are placed outside the microcontroller. You may have an external EEPROM, you may have an external flash, external CAN controller, external maybe some storage, additional storage if you want, right? Maybe some DIO extension pins, or maybe some kind of actuator sensors which are located on a PCB but not part of the microcontrollers, right? How do you access this? There could be a lot of sets of transceiver, CAN transceiver, flex rate transceiver. All these transceivers are located outside the microcontroller. So how do you control this piece of hardware, right? So to control that, you would need a ECU abstraction layer, right, which has this functionality inbuilt where the code is written to control these peripherals, right? So the guy who is in the ECU abstraction layer, right, for him, he really need not to worry about whether the CAN controller is internal or external. For him, it is just as simple as send a CAN message. And the ECU abstraction configuration or the implementation will figure out whether my CAN controller is internal or external, and it will decide its flow based on that, right? But the person who is above, who is calling the ECU abstraction layer, for him it really doesn't matter, right? So that is how the task, if you come here, make higher software layers independent of the ECU hardware layout, right? You have a two ECU hardware layout, one is with the internal CAN and one is with the external CAN, right? And for both of them, the above layer is not going to differentiate. It's not the headache of the above layer to figure out whether it is an internal and call a different API. CAN underscore TX underscore external, CAN underscore TX underscore internal. We don't have that kind of, it is always CAN underscore TX, yeah. And the ECU abstraction layer configuration or the implementation will decide how the further signal or the flow of the software should happen. Coming back quickly to the properties, implementation, yeah, it is a microcontroller independent, definitely, because all the dependencies taken care by the MCAL. So it is independent of the microcontroller, but it is a ECU hardware dependent, right? The implementation of this depends. If you have a CAN controller or the EEPROM externally put or the internally put, the implementation is going to change how you're going to access it, right? The implementation is independent of microcontroller, but it is dependent on the ECU hardware. Upper interface, definitely it is a microcontroller ECU hardware independent, right? As I told you, the layer above ECU abstraction, he need not to worry about which controller it is or whether the CAN or the EEPROM is inside or outside, right? So he's completely independent of the ECU layout. Hope this is clear. Yeah, next we'll quickly take a look at complex driver, right? So complex driver, this is a place inside Autosar, okay, where you can support a non-Autosar functionalities, the functionalities which are not supported by the Autosar standard, right? So if a tomorrow customer comes and he says that, hey, I want to have some Bluetooth stack or maybe their own driver stack, right? As a part of the product, you cannot say that, hey, I'm building Autosar product and I cannot support because Autosar doesn't support it. No, there is a place to support such drivers, which is called as the complex driver, right? And the reason why you have all these layers given a certain shape and a certain position, which says that whether it has a direct access to microcontroller or not. So if you see here, MCAL is directly sitting on top of the MCAL, and that's the reason it has a direct access. Whereas the ECU abstraction layer, it does not have a direct access to microcontroller. It has to go through the microcontroller abstraction layer to access the microcontroller. So similarly, complex driver, if you see, it is like put vertically, it can bypass MCAL, ECAL, and it can have a direct access to the microcontroller, right? So there are basically three reasons why do you need a complex driver. So first one is the drivers, the device drivers which are not specified within Autosar. You can come here and you can develop your own drivers. Autosar has a certain template or the specification or the template specification given. If you want to write your own driver, how should you write it? You can follow that and you can write your own drivers, right? And there are some situations, maybe I'll just give an example. Maybe if you want to open an airbag, right? You have processed everything and you want to quickly open an airbag, and you have application software running which is sitting here, and it want to send a message which goes to the RT, right? It comes to the service layer, from service layer to ECU abstraction, then the MCAL, right? Then goes to the microcontroller, puts a particular pin to off to on, and then the airbag opens, right? This is going to take tremendous amount of time, right? When I say tremendous amount of time, it's just a few microsecond or a millisecond, but that's a tremendous amount of time when it comes to opening of an airbag, right? Right, or maybe if you want to control the accelerator pedal signal, which is again you need immediate torque when you press the accelerator pedal, right? So how do you bypass all these layers to get the timing requirement correct, right? So there are certain features which demands very high timing constraints, right? So when in that case it is not practical to go through all these layers, because that's going to add certain delay, because it is all the standardized software and you cannot jump the layers. You have to call APIs by APIs, and that's going to increase the stack consumption. Maybe in other words, it's going to increase the number of CPU cycles. In other words, it's going to increase the number of microsecond or the millisecond it is going to take to achieve the functionality. So you want to cut down that, so you can take this additional path, so called as complex driver, and achieve the very high timing constraints or the requirements. Yeah, that is the second purpose. And the third purpose is the migration purpose, right? So today you have a CAN driver with you, which is not built as per the Autosar specification, right? So you cannot like build it for the Autosar and then integrate. You can always put it in a complex driver in its original form and make it working, and then slowly start porting each one by one app or the one by one APIs or the one by one modules or the sub modules what you have inside that, and make it as a Autosar compliance, right? So yeah, that's the third reason. So just to repeat, yeah, the which are not specified within the Autosar, you can write inside the complex driver. Anything which demands a very high timing constraints, you can use the complex driver. And for the migration purpose from non-Autosar to Autosar, you can start from complex driver, right? So these are the three tasks which complex driver has, and the properties might be application, microcontroller, and ECU hardware dependent. So he does not really say that okay, it might be, right? Again, it depends, right? So if you're writing a driver for a component which is only present on that particular microcontroller, right? If there is a small, maybe a crypto CSM or maybe some Bluetooth, right, which is only present on that microcontroller, definitely it will make the hardware dependent. Upper interface again might be, because the name of the interface what you are giving there, yeah, that could be dependent on the hardware what you have underlying inside the microcontroller, right? It is not something which is standardized. So the upper interface name is definitely gonna depend on the driver for which you are writing, the component for which you are writing the driver. Okay, quick time check. Okay, so, yeah. Coming to service layer, which is the heaviest layer inside the BSW, which houses various functionalities, even including the operating system, right? It has the operating system, it has the vehicle network communication management and services, it has the NVRAM management, diagnostic services, ECU state management, mode management, right? Your crypto services, all these services are located inside the service layer. Maybe to simplify it, it has all the services. When I say service, right, all the below layers, they just operate in one way, right? You ask them to do certain thing, they'll try to do that. But whereas service layer has some intelligence built inside that. It has some basic intelligence, or in other words, maybe a state machine built inside it, where it can take certain calls. For example, if you want to write into a non-volatile memory, right? So non-volatile memory is accessed by various modules inside the ECU, right? And how does this non-volatile memory manager or the service NVRAM service works is, yeah, it has this intelligence built in where it can take the service, it can process it, it can put it in the queue, and it can go and write into the NVRAM and then write it to the ROM, EEPROM, right? And if it writing fails, then it can retry. And if how long it's going to retry, so there is a maximum number of attempts it has to retry. It will retry so many times. If it still fails, what it need to do? Can it write some default value? Right? Can it mark that particular element as invalid? So all this fail-safe mechanism, the state machine, the retry, the intelligence, everything is built inside the services, right? Whereas the below layers are the standard APIs. Through calling those, you will get to write into a EEPROM or read from the EEPROM. But the service owns furthermore functionality of this state machine implementation, where it can maintain a different state, busy, free, in queue, even do the arbitration, right? In terms of different calls, who gets the more priority when you're writing into the EEPROM, or when you're sending two different kinds of messages, right? Or when you're two components trying to access some particular resources. All this logic is put inside the service layer. Also, it kind of has some ECU level controls, like ECU state manager, which is responsible for basically managing the complete state of the ECU. Right, you also have the operating system itself. You can also see this L shape which is landing onto the microcontroller because of this operating system, right? So the operating system, what Autosar suggests or has in the specification, is the OSEC, right, which is a real-time operating system. Okay, and basically does not have any so-called software scheduler. It is mimicked with the hardware, where you have a hardware interrupts timer interrupt which calls one by one and executes your different procs, right? So if you studied OSEC, if you go back and study OSEC, you'll understand how it works, right? So OSEC is a choice of OS, what is being referred here, specification, OSEC specification, okay? Implementation, yeah, it is mostly microcontroller and ECU hardware dependent, yeah, because it is sitting on top. The word mostly is coming is due to the operating system, which is kind of running on top of your microcontroller. So that part is only which gets affected, whereas the other communication services, diagnostic services, crypto services, non-volatile memory services, all these services are independent of your ECU. Whereas the upper interface, it is completely independent of which ECU or which microcontroller it is. It does not really matter, and it is completely independent. So now by the time you reach the service layer, you see that you are independent of both the microcontroller and ECU hardware. Okay. So above that layer, you have a runtime environment, which is basically responsible for differentiating the BSW and the ASW. So anybody who want to talk from ASW to BSW, it has to go through the RTE. So RTE is nothing but a runtime environment, which helps different software components, or a software component and a software module. When I say a software component, I'm talking about a software piece of software inside a ASW. When I call it as a software module, I'm talking about a module inside a BSW. So if the two software components want to talk to each other, they have to go via RT. If a software component want to talk to a BSW software module, it has to go through RT. So RT is nothing but in a simple words, you can think like a postman. You hand over a message to him and he will deliver it to where it has to be delivered, right? So, and this is the only piece of software which is fully generated. It is fully generated, right? So if you create all the interfaces, right, when you create a center port or a receiver port, if you can create all these ports and give this information to the RT generator, it can actually generate a RT.C, where you can see that how two software components, or a software component and a software module, is interacting, right? And this RT is completely dependent on the ECU, and this is not something which is dynamic. Every time a software interface changes, you have to regenerate the RT, right? So the RT what we have, it is a static RT. It needs to be regenerated every time you change the software interface. If you change the functionality, you need not to rechange, yeah, and need not to regenerate. Coming to some of the tools what is used, I have just taken this one from the vector. It has all the vector tools mentioned here, but at the same time, I'll also try to give you other options which are available in the market, which you can use it. Okay, so this is the complete software development cycle. Okay, we have a bunch of questions. I'll take all of these questions at the end of the session. Okay, and we'll try to address that. Whatever questions you have, please go ahead and post it, and we'll take maybe the ones which are very common. We'll try to take those questions. Okay. So this is the V model. So we always start with this software design architecture or the requirement, right? Which is Prevision is a tool which is helping a lot of OEMs where they can manage all the software components requirements, which can be placed inside this Prevision and managed, right? On a just pull and drag, you can take the functionality of one ECU and take one issue from one vehicle and put it into another vehicle. It does not only resolve the dependency of an interface, hardware component, wiring harness, but it has a lot of variant related information. It is humanly impossible to manage this information without the tool for an OEM, and they need a very strong tool where they can resolve all this dependency and seamlessly handle all these so-called lacks of interfaces, right? And the prevision is the one tool which is helping them to do this. There are a lot of other tools which OEMs have developed by themselves in-house and they use it. So we virtual target at the requirement side. Mostly, sometimes OEMs use it to ensure that they have a software component design created which has the meaningful interfaces, which means that every interface which is sending a certain information is being received by another software component, right? So there is a logical end to every transmitter and receiver, right? So at a software component level, you want to ensure that the design which you are handing out to tier 1 for the implementation, that is does not have any loophole. And the Davinci developer is a software which is used for the software component design itself, where you can create a sender port, receiver port, client server, and generate this skeleton code, which has just a header, right? The function names, arguments, and the return type, and the blank body, where you can go and write your code. Either you can write with the hand, or if you are somebody who is using the MATLAB Simulink, right, you can generate that code and you can place it there. Then comes the Davinci Configurator Pro, which is your BSW configurator. All the modules, the layers, what we so far saw there, that can be configured and generated for a particular customer or a requirement or a particular ECU. So you also have a lot of tools here. The vVirtual Target has this equivalent, your target link, the tools from the ETAS, right? Tools from the ETAS is one guy, MATLAB is one guy, Target Link is one guy, who are providing the solutions equivalent to vVirtual Target. Davinci developer, we have a electrobic toolchain which have the equivalent WinCore EB Tresors, right? Which can be used there for the Davinci developer and Davinci configurator. Yeah, ECU works is something which I think some of the specific OEMs use, right? We have a vVirtual Target again coming into picture here, but here it is not at the interface level, but you can actually simulate all the drivers what you have generated without the need of an actual hardware, right? You can test the functionality of that. Kano.amd is on Autosar monitoring and debugging is a separate module inside the Autosar stack, using which you can, without the need of actual debugger, you can take a look at certain variables or the messages and you can monitor them, or you can use it for the debugging. The Kano is your system test tool where you can actually completely debug the vehicle network, right? Where you have like a CAN link, FlexRay, Ethernet, most all of this is supported by the Kano tool. You can load the CDD, DBC, you can do your COM stack and DAG stack testing, even the software download, upgrade, all that can be done here. Then you have the calibration where CAN-APE or the ETAS equivalent tools you have, which you can use like a Inca. Kano equivalent, you have a USB CAN, right, tool which is available, which you can use, which is a low cost tool. Interpreted system has their own tool, right? So yeah, these are the various tool chains which are part of the ecosystems, and each tool demands a certain knowledge before you use it, right? If you are going to use developer or a configurator, you need to know Autosar. If you're going to use Kano, right, you need to know the underlying protocol, whether it is a diagnostic protocol or a Canon protocol, right? So these are the tools or the technologies what you will be surrounded with when you start working into a Autosar project, and it is the basic need. Any automotive engineer who is willing to join a OEM or a tier 1, the first expectation is, there is a checkbox, right? There is a checklist which you need to fulfill before you call yourself as automotive engineer or Autosar engineer. So we are here to bridge that gap, trying to help all the embedded engineers or a good embedded C engineers who can transform themselves into automotive engineer or Autosar engineers, so that whatever in the market today we have a shortage of automotive engineer or Autosar engineer, quality engineers, we can fulfill this gap. The one USP from our side what we have is, it is not going to be only theoretical sessions what we'll be covering in the actual training. It would be 60% hands-on and 40% theory. That's what we believe in. There are a lot of study materials, videos available which you can go through, but you'll never get that confidence to go on to a project and start contributing or working on it. Right here, we are going to go through all the tools possible, right? Including the configurator or the developer or the Kano, right? Your CanDB, lot of tools which are required to build a product, right? So we are going to go through all those tools. Every participant will get an access to this tool and where they go and implement this. And there are a lot of real-time examples, industry examples we take and we try to build, and each and every participant has to build it by themselves, right? They have to finally generate the RT and show that the code is running. So at that is the level what we want to kind of cover in the training with 60% of a hands-on, so that enough time is spent on the tools and the actual configuration rather than going through the slides or the material, right? Yeah. So if I stitch all the layers, so for what I shown, this is what the architecture looks like: the complex driver, the MCAL, ECAL, service layer, RT, application layer, right? So now, as an automotive engineer, do I need to learn all of this? Do I need to expert all of these layers? No, it is not required. So you should have a very good understanding of this, okay? How the different layers are divided into different stack, MEM stack, right? You have a wireless communication stack, com stack, IO stack, complex driver, right? So you should have a very good understanding of all these different modules, but you can pick your vertical, right? You want to be a com stack guy, or you want to be a mem stack guy, or crypto stack, right? So then you should take this vertical as a one of your specialization, right? So com is something which you can specialize in, and again in the com, right, you have a driver, you have abstract service, right? So you can pick which one, maybe driver, right? Like you want to expertise all the communication driver, maybe CAN, LIN, FlexRay, Ethernet, right? All these drivers you want to expertise. So then you can focus more on the drivers itself, or maybe in other words, in the memory driver, maybe EEPROM drivers, you have flash drivers, you have flash emulated EEPROM drivers, you have RAM test units, right? All diagnostics units for the memory related. So in the wireless, you have again various so yeah, basically you can decide. First, you need to get a complete overview of what is Autosar. And again, these modules, right? Again, there are sub modules inside this. So you need to know all of that, how they work, how they interact, what is possible, what is not possible, and then choose a one vertical and develop an expertise on that. And then choose one particular block and try to, so specialize on a one vertical and pick a block and expertise on that. So it is a very long journey. It is not something which we can cover in one session and say that okay, you are an expert, but it is a very long journey. So we don't want to do it in a one session or a two session. So that this training is going to be a complete 1 month training, where we engage few hours on a weekday, and we will engage on a very long full day sessions on a weekends, right? So that we are in continuous touch for 1 month for this knowledge transition. Quickly coming back to interfaces, we have a various interfaces: Autosar interface, Autosar standardized interface, then the standardized interface, right? So these are the different, I think we are almost done with the time. Quick time check. Yeah, so various interfaces, there are 3 types of interfaces. Autosar interface is one. Just to give an example, if a software component is talking to another software component, nothing is standardized there, but they have to use the Autosar interface. It means they have to go through the RT. So I would call that as an example for the Autosar interface. Standardized Autosar interface, the word moment you see the standardized, it means that this particular interface is documented. And the moment you see the word Autosar, it means that it has to go through RT. So if a software component want to talk to a software module, that is the example for a standardized Autosar interface. What is standardized interface? You don't see the word Autosar, right? It means that it does not need to go through the RTE, but at the same time you see the word standardized, which means that it is specified in the Autosar specification. So for this, you can think a software module talking to another software module is a standardized interface, which is in the between the BSW software components. Okay. So that is about software interfaces. So here, if you take a software component, we have a different runnables. Runnables is nothing but your smallest entity which can be scheduled inside operating system. So it can run as a init runnable, or it can run every 10 milliseconds. You can configure inside a task, and you have different ports which can be configured. You have a R port, which is called as a receiver port, which is used to receive some message or information. You have a sender port through which you can send particular message or information. Just for an example, say engine RPM, right? So this, if you want to send the engine RPM, you can publish it to the RT, and RT can make it available to other guys who are willing to receive this information, right? So that is the sender and the receiver port where the information exchange can be done. And you have a client and server. So it's always not that two software components or the software component and the modules want to exchange the value or the information or the variable. Sometimes they want to call the functionality of a one software module from another software module. You want to basically achieve a RPC, remote procedure call, right? How do you do that? So that is possible with this client server mechanism, where you can configure the servers and the client. The client can call a function or a procedure which is residing inside the server, right? So server is the one who is having the implementation of that function, and the client is the one who is caller of that particular function. So this is what is the symbol for the client, and this is what is the symbol for the server. So when you're defining the software component, so you'll be basically defining the interfaces and the runables, and you generate the code, which is the empty functions, and you go and you write your manual code inside this. So this is what is application software side. But whereas BSW, you will mostly write, you will configure and generate the code. We'll take a quick one example as we are trending towards end of the session, right? So let us take this example, okay, where we have a light management system. We want to turn on a particular headlamp of a car. So we have a knob, we have a headlamp, and we have few sensors. We'll take a look at it. How does it work? So I rotate this knob. The moment I rotate this knob, a DIO pin detects that I have rotated this knob, and the microcontroller abstraction, through the ECU abstraction layer, the information goes to one of the software component, which is called as a switch event. So switch event is a basic software component. Any change in the switch position would be captured by the switch event. The moment switch event captures this, it will analyze what kind of switch event it is, right? Here you will see different switch events, right? So here right now it is a light request switch event. So light, it will call a light request, and light request will evaluate what kind of light request it is, right? There are again different kinds of tail light, front light, interior light, boot light, right? So it is a front light. So it will send a message to a front light manager through Autosar interface asking for a key position. So now it want to know what is the key position, because the key position, maybe today's time we have the DRLs, which is always running. But if there is no DRL, first you need to understand what is the key position. If the key position is in the right position, then only you are allowed to turn on the light, front light. Okay, so you check, you send a message via CAN driver, you try to read what is the key position, you read it, and if the precondition is set, then you do the set light and turn on the headlight. To turn on the headlight, you again send an interface, you call through the RT, come to the ECU abstraction, go to the PWM. So PWM is again a driver which controls the pulse width modulation. Higher the duty cycle, brighter the light, and you can turn on and control the intensity of a light, right? So all of this happens. You need a DIO, PWM, CAN driver, ECU abstraction, RT, and 4 different software components with the functionality and the OS, and all of this is required. Just to a simple action.